Yeah, I think I'm not able to start the live stream, so I'll instead
Yeah,
record the session.
audible, sir. I think you and me are also only there. Maybe people are busy somewhere.
Right, right. Probably because of the festival.
I'm lucky. I'm lucky. One to one to you.
Right. So let's so week 7. Let me just share my screen also.
What is there? Living seven. I have not gone through because
Week 7 is greedy algorithms and
okay.
AVL trees. Can you?
Related to graph only, na? I will be able to understand, no? Because I know graphs, so I will be able to grasp.
Yes, yes. So I'll first explain the concept and then we can solve.
It is better because in the night I will sit and to go through the lesson because I have holidays.
Okay.
Tomorrow is the holiday, and after Saturday, Sunday is that. But Java OPP is there, so I have to sit. So please, uh, just think that I have not gone through the videos. Honestly, I am saying.
Yeah,
So
yeah, no problem. I'll first explain the concept and then we get using that concept, we'll solve.
yeah, yeah, please, please, thank you.
Look, you can see the screen, right?
Yeah, I am.
So PP1 is about Huffman's coding, and PPA2 is PPA2 is minimizing lateness. So these are the two topics. So before I begin the question, like start the question of PPA1, we'll just cover what the greedy algorithm of
Yeah,
Huffman
yeah,
coding is.
yeah. That's I wanted to know because without that, the coding part I will not understand.
Right. So do you know what greedy algorithm in general? What is it?
Videologism, what I understand is that he, where we need some goal. Suppose we need shortest path or minimum spanning tree. For that purpose, if we need the minimum weight of age, so we just find the code to get the minimum uh, edges, which is having lowest weight. And the
Right.
shortcut for that is the utility. It is like that. What I understand.
Right.
Huh?
Yeah, yeah, oh, yeah. You're almost correct. So, like the name itself suggests, it has greedy in it. So this is
Yeah,
like
it is synonymous. It is synonymous with the name.
right, right. So it is like an approach to generally we use to solve optimization problems, such as minimization or maximizing a certain quantity. We usually use this by making locally optimal choices at each steps. So when we see locally the neighbors of something or something, we in that local part we select the best possible option that is available at that moment. We do not think it as a whole. Instead, locally we select the best possible option available at that time, and then we forget about it. So this approach in
Yeah,
general is what is the greedy algorithms use.
runtime at the runtime.
Right, right. While running, they see the local best possible option and select it then and there itself, and then we do not turn back to it.
Right. Okay.
Okay, so yes. So this is the general what greedy algorithms are. So now regarding Huffman coding is one of the greedy algorithms. So let's just go through the slides. So this is like generally not any language we take English, Hindi, whichever language we take, we encode the alphabets to say as zeros and ones. So binary, we try to convert it into binary. So like there are 26 letters in English alphabets, right? So we will need a binary string of length 5 to cover these many alphabets. If we use A to Z, all the alphabets, we'll need so many binary strings, right? To encode the if you take English language using zeros and ones.
Yeah.
So this is not a very effective way to have a binary string. So so what we are trying to do this better in a better way. So first, are you aware of this Morse code, dashes and dots in the army and all they use, right?
Morse code.
Yeah, so it is basically it has dashes and dots. Dot you can say it is zero, dash you call it one. So we encode using these zeros and ones. It is binary itself, but it is Morse code is generally used in dashes and dots when we write it or send a message. So this for example in this encoding for E, if we say zero, for because E is a very frequent alphabet, so we give E as zero, T as one, and A as zero one. If we say, for example, this is what we are using, this is what the encoding we are using for. So how do we decode this 0101 is a encoding we have used. So with this data, we can how can we decode 0101? So we can say, right, E is we have seen E is zero,
For zero. One is T. ETA.
ETA. ETA is one possibility, but we can also we can call it double A, right? Because 01 is A, so we combine 01 as A and another 01 as A. It can also be decoded as double A. Similarly, ET we can also do, right? ET.
Okay.
So this is a problem. So generally in Morse code, there is also dot, dash, and a space. So that space indicates the separation, the boundary between. So it usually, if it is a double A, then it will be 01, a small space, and 01. So that is
Hmm.
usually how Morse code works. But so you see that we need a boundary also, right? To separate, to figure out what is the how to decode.
Separator is required.
Right. A separator is required. So how can so without use separator is basically a third. So a third so like 01, that separator we can also consider it as a third part of the encoding, like dot, dash, and the separator. So that is also a letter.
Part of the coding, right?
Yeah. So right. So without using that, how do we encode? Is like so is the under like that is how we come to this Huffman coding. So instead of using that space or some boundary, we are trying to encode. So let's take this example. So like we said, so if we for example say A is double one, B is 01, this C is 001, D is 10, and E is triple zero. If we use this logic, will we able to decode this without the boundary? So if we see zero, we do not have a value for zero, right? There is no zero, no alphabet corresponding. The encoding of no alphabet has zero. So if we start from here, we start decoding from
Single.
here.
We are talking about single zero.
Yeah, like let's start decoding this string. Okay, let's do it here. I'll just
Yeah. I mean,
okay. So this was that example, right? Now now this is a prefix code. I'll start with an example and then explain what it is. Okay, so let's try to decode this using this information. This is the information we have. A is so and so, B is B, C, D, E. We have five alphabets and its encoding. So let's try to use this and decode this particular message. So let's start from here. First, we have zero. So there is nothing corresponding to zero, right? No alphabet corresponding to just single zero.
CECAB.
Right. So yeah, you're right. So 00 also there is nothing corresponding here. So when we come to 001, we have C. That's what you said, right?
Yeah, that's why. Yeah.
Right.
See.
C. Now the next stop will be here.
E. Because
And
we have no option other than this. Only this option is available.
correct. So next will be
C,
C,
A,
A,
and B.
B. Right. So this is a prefix code, what we call. So in general, prefix code
What you
is
mean by the prefix code is that already you have fixed the code for the letters we want to encode. Then that is why it is called prefix code.
no. So not like that. So we will not like we have to fix these encoding such that there is nothing prefix. So like encoding where for any x, the encoding of x is not the prefix of encoding of another y. So if we take a, so a is like 1 1, right? The encoding of a is 1 1. There is no prefix such that you can. So if we just take 1, for example, so uh, here we have let's take c. C is 0 0 1. So prefix of this encoding, so 00, this is the prefix. This 00 is not representing any other alphabet, right? So encoding of C, so this encoding of C is not the prefix of encoding of any other alphabet. That is the prefix code. We have to choose the encoding such that the prefix of like any prefix we take 0 or 00, these does not correspond to any other alphabet. So that way, when we start with this string 00, there is we know at 0 0 1 we have to stop because there is a corresponding alphabet to it. So that is how without the boundary, we already know the boundary here because this is the only one. C is the only way. Once we see 0 0 1, we know it is C. We automatically find the boundary there. This is the prefix code. So there are like no overlaps. Uh, is that logic clear? I hope you are able to understand this one. So this is the prefix code. Okay. Let's now move on to like this is the example of prefix code. Now let's find the optimal prefix code. So let's, for example, if we take let's take this example. And let's say in we have a set of string. We have, for example, a set of string. Say A B. Okay. So these are we had A B C D E, right? So we have this string A B B C C A E. Suppose we have a string like this, and we want to try like decode it in an optimal way. So how do we do that? Is the next part of the slides. So what is the frequency of, for example, A in this string? So it is occurring 1, 2, 3 times, right? Out of 8 alphabets, A happens to be 3 times. So the measure of frequency, we have to measure the frequency of each letter. That is the fraction of occurrence of X over a like entire string. the number of time x appears divided by the total number of letters. So the frequency of A in this example would be 3 by 8, right?
How
A
how
happens
how it is?
because the total count of this string is how much?
Three.
Length of the string.
Length of it is, yeah, 8.
8, right? Yeah. How much time? A occurs 3 times, right? Count of A.
Okay, okay, 3 out of it, right? Okay,
Yeah.
okay, okay.
So the frequency is 3 by 8. Total number of times x appears divided by the total number of letters in that string.
Yeah, yeah.
So suppose so there are like so f of x is basically the so this is basically the probability. So if we this is just the probability of A, right, in the string. How much time A occurs in the total string. Okay. So these are theory. We'll come to this. Let's try do an example first. These are theories. We'll come to it. So these are just I'll first explain the example. Okay, so this is for example, say the like before we had the alphabets A B C D E, and its encoding this one, and let's say the frequency of occurrence of A B C D E is this. So if we see the frequency will always sum to 1. If we add this up, you will get 1 as the answer. So this is like the percentage of A occurrence, like in the total in the string, how much time A occurs, that the percentage is what is given. That is the frequency, basically.
What is this
Uh,
E of, is a function, EX.
yeah, that is the encoding of A. So this is given to us in this example.
Okay, it will be given.
No, in this example, it is given. Using Huffman coding, we are supposed to find it. We are supposed to find the best encoding possible. But in this example, it is given. Let's say E of x is the encoding of A. A is represented as 1, 1. B is represented as 0, 1. C 0, 0, 1. Like that.
Yeah, yeah.
Right. So now how many bits are used to represent A? 2 bits, right? 1 and 1. 2 bits. And B is also 2 bits, C 3 bits, D 2 bits, and E 3 bits. So this is the average number of bits per letter. That is the frequency into the number of bits. So A has 2 bits, so 0.32 into 2, 0.25 into 2, like that. We see the average number of bits. If we sum this up, we'll get the average number of bits is 2.25. So the fixed length encoding, that is the first encoding which we saw, that has like in this range. If we see A, B, C, D, E, that is 3, 4, 5, 5 alphabets, right? That will come in this range. So that will require 3 bits per letter. If we go to the fixed length encoding, that is, if we fix so many bits initially, then this is the range. You will require 3 bits per letter, right? So using this method, we are able to like 25% save the space. Since for A we have used only 2 bits, and if it was a fixed length encoding, then it will be 3 bits per letter, right? Uh, 1 second. Yeah, I think I forgot to explain what variable length and fixed length encoding is. So basically, fixed length encoding is we fix the number of binary string that is required to encode the set of alphabets. So if there are like 26 letters in the entire English alphabet, we fix the 5 bits per letter alphabet. So that is the fixed length encoding. So in variable length encoding, what we do is uh, we map using that frequency. We map if a particular we map a certain set of bits accordingly. The because we see the frequency, and accordingly we map how much bits is required. So it variable length encoding basically it maps those symbols to a variable number of bits. So you can see now it is not fixed. Some are 2 bits, some are 3 bits. So this is the variable length encoding. And fixed length encoding, we fix so much bits per letter. So all the letters will have so many bits. I hope that part is clear.
All letters will have same number of bits.
Yeah,
Arithmetic.
right. In fixed length encoding, it will have whatever. And so, for example, in this case, we have A, B, C, D, E. That is five alphabets, right? So we can represent 5 alphabets using this in this range itself. All right, you will need uh, three encoding whatsoever. Like whatever we use, we will need 3 bits per letter. So we fix this three. So all the A, B, C, D, E, all 5 of them will have encoding of length 3 instead of this 2 here. That is fixed length encoding. So using this variable length encoding, we save much more space because we use uh, variable. So this is 2 bits and this is 3 bits. Only that some of them have more bits, some have less bits. So when we actually encode the initial strings, like for example in this string we encoded, right? In this case, so if we had used the fixed length encoding, A and B would also have been 3 bits. So this would have been 3 bits, and this would also have been 3 bits. So it would have been 2 more extra bits. So using this variable length code, we can save the space in general. So that is the variable. So use of using the variable length code. But we can also do a little better than that, even better. So if we see the frequency, right? So in this case, if we just the highest frequency is B. So we have one, two, three 2 bits encoding, right? So if we give these the smaller bit encoding to the highest frequency, so that is since A is the highest frequency, A happens 0.32 times. So the number of A's in the string is more. So if we represent A using just 2 bits, so when we encode, we save more bits, right? We save more space. If we give the smaller bits, the smaller bits per letter to the higher frequency alphabets. Are you understanding this point?
Yeah. Just
Right. Yeah.
yeah. Got it.
Okay. So this is a better way to encode. So we first decide on this. So here
It
we
is
have this.
better. How can we say it is a better way?
So if we see these two examples here, uh, so C was using 3 bits, right? And the
Yeah.
frequency of C was higher.
Yeah.
But when we since frequency of C is higher, we shifted the C and D because so now the frequency of C is higher and the number of bits is less. So if you see the average number of bits per letter, if we use this formula again, we see a reduction here, 2.23. Here it was 2.25. So there is some number. So the average number of bits per letter is reducing. So isn't it a better encoding?
Frequency reduced. Where it is reduced? 30 to 528.
So
Frequency reduced.
basically, what I'm saying is, if we have a string like this, so if we have a string and we see which are the highest frequency, so we have to first use the prefix code, right? So for example, in this case, we have 1110 and I mean 01 and 10. So we first see A, B, C. There is no D.
ABD.
So let's
There
say
is no.
there is a D also in this example. So this we so here we first calculate the frequency of each. We calculate the frequency of A, we calculate the frequency of B, and so on. C, E, and D. And then we see whichever has the highest frequency. If the frequency is higher, that implies the count is more, right? That is so that alphabet is the count of that alphabet is more. Basically, that is what's saying. So if the count of that alphabet is more, uh, so we we give the lesser bit encoding to that alphabet. So in general, so the length of the decoded string will be lower. If we do this way.
Yeah, yeah. Got it.
Right. So that is how we. So this is the general idea of how Huffman coding. So now we need an algorithm to come to this, right? Like how do we code this? So let's say we. Let's just so all the we represent the all like a binary tree. We had the tree, right? So we encode all the alphabets as the leaves of the tree. Like path. So so letters are basically leaves of this tree, of this binary tree. If you see, okay, so so are you understand like why? I will explain why this is so. So this is the we start like this, okay? We give so okay now. So let me just one second. Just give me a minute. Okay. So let me pull this up. Right. Okay. So if we see this,
Hi, sir. Sorry to interrupt. I was waiting for the YouTube stream. It's not streaming there, sir.
yeah. So what happened is I'm unable to start the YouTube recording right, live streaming right now. So
Okay.
instead I've recorded it and I will give it to
Later
another.
it will be available, you see.
Yeah. Yeah.
Okay.
Later. Okay. So let's get back to it. So if you see this
बताइए सर,
setup, yeah.
हैप्पी हो रही सर, आप निकल रहे हैं ना?
Uh, I think Srikanth is not muted.
अच्छा लगता है और दिवस हैप्पी जर्नी.
Okay. Srikanth, can you mute yourself? Okay. Okay. So now let's say let's try to let me bring that table also.
Sorry, sir, somebody came.
Yeah. So this was the table, right?
Yeah.
Yeah. Okay. So this is the table we had. So let's give these. So let's say this side is 0 and this side is 1. So this is 0, this is 1, this is 0, this is 1, this is 0, and this is 1. So this way, if all the encoded values are sitting at the leaves, so in this way, no encoding leads to another encoding. That is, that overlap will not happen. So if we see A was 1, 1, so if we come this way, then A is equal to 1, 1. Similarly, B was 0, 1. B was 0, 1. And E was 0, 0, 1. So this way, we can represent, like in this binary tree, we represent the prefix code in the binary tree this way. So in this structure, since all the encoded value are on the leaves, since they are on the leaves, so there is no overlap like we had before. That overlap is not there. So no encoding will lead to another encoding, right? So no encoding is basically a prefix of another encoding. If we represent all of them in the leaves of a binary tree. So this way, using this binary tree, we can actually find out the encoding of we can encode using this binary tree. This is a way of doing it. Like in the Huffman, this is how we do it.
This is what is the table is given in the previous one. Sir. We are doing another way.
No. I was just showing, like, this table is actually, I was just showing how, even if in this encoding, if you see, if we just go on 0, 1, 0, 1, we see like all the left side of the binary tree, if we give it 0, and right, if we encode as 1, so we can get the structure, right?
Yeah. So 0 is the way edge 0 or the node 0.
Edge, the edge we are calling. So this path so this path, if we say from the root we go to the left till the leaf, the path we follow the as 0, 0, 0. Yeah, the edge, you can call this the edge. So the left edge is 0, right edge is 1, always. So if you want to reach C, we come like this. That will be 0, 1, right? So
Yes,
this
I
is
got it.
so representing these alphabets as the what do you call, leaves of the binary tree, we are able to come up with this encoding. That is, there will not be any overlap, and so using this we can actually come up with the Huffman encoding, because there is no overlap if we represent as the leaves, right?
The
So
path gives the code and the leaves gives the text we are encoding. Is it so?
yeah, only in the leaves we keep the alphabets.
Yeah.
So there are certain properties I will come, like, so let's just see
The
these.
code of that and the code of that alphabet is lying between the path of that node, right?
Right. So if we come that path, if you follow that path, you can see what the encoding is.
Okay.
Okay, so there are a few claims as well. That is, any optimal prefix code, this tree will always be a full tree. That is, the child of all so there will not be any node with one child. So you can see, right, all the parent nodes have two childs.
Complete binary tree. What do you mean to say?
Right. Not complete. Complete means even all these will have children, right? This is not a complete binary tree, but no parent will have one child.
Okay.
So if you see why that happens, so if you see any child, if you take this example, uh, if we for some case, if we remove this d this node, if there is d no, this node is not there, for example, if you see, then this one will automatically get promoted here, right? We can directly give e here and use this encoding 00.
Okay. Okay. Thanks.
Right. So that is why we will always have this property. Otherwise, we can just straight up promote. So that is one claim. And then the claim two is in an optimal tree. X is at a smaller depth. Yeah, the frequency. So this is how we create this tree. So if the frequency of X is greater than Y, so for example, in this case, if frequency of A is greater than frequency of E, right? The frequency of A is greater than the frequency of E. So A will
Yeah.
come above E. So like only two represented, like two bits is used for A, right? So if the frequency is higher, then that node will come above the node which has lowest frequency.
Yeah.
Higher or equal. It will either be higher or equal in the same length. That is the next property.
And what was the first one? Optimal prefix code produces a full tree. Means the last one should be having the in the leaf nodes. We should have the uh, characters. Is it this one?
Right, right.
Claim one.
Yeah, I think you said it will be a full tree. You said right, and I said
No, difference between full tree and complete tree. What is I mean? Last nodes are having the values, then it is a full tree.
right, right. So if there are like no child, there are if there is either it has to be zero or two children. Oh, that is the definition of full tree. I think so that is the definition of full tree. So a node has to have either zero or two children, either no children or two children.
Got it. Got it. Then it is a full tree. Good.
Yeah, then it is a full tree. What you said before was right. Okay, so so these are the claims. An optimal tree for any leaf at maximum depth. Uh, its sibling is also a leaf X. Okay. Okay. Yeah. So basically, there will be a sibling at any depth, right?
Yeah. Yeah.
Yeah. So in the maximum depth, wherever the maximum depth is, it will also have a sibling. Is basically what this claim is saying.
Yeah. If it is a full tree, then it must have a sibling, right?
Right. Right.
Because always two will be there. Okay.
Right. Okay. So these are the more theory of it. I think I'll just explain the code how it is. So these you can watch the lecture. These are theories how it is done. So this is explained in the lecture. But I'll explain to you how it works. How can we use the algorithm to like encode an alphabet using the frequency? Okay, if we are given a string, how to use that to do this Huffman algorithm? So let's say so. This was the example. So initially, so this is for example, we are given a like we said before, we are given a string. So we actually calculate the frequency of each alphabet and we record it, right? Then what we'll do is uh, we'll combine the lowest two frequencies together. So D and E are the lowest. So if you see the frequency of D is 18, the frequency of E is 0.05. right? We combine these two together and we get the DE as point. So we add the frequency as well. So what we are basically doing is we are in this example, we see the frequency. The frequency of E and D was the lowest. So what we do is we combine it together and we, so this was B, A, C, and we create a node like this, ED, right? So we combine these two nodes together and they create a combined node, adding the frequency of it as well. Okay. Why we are doing this, I'll explain. Similarly, in the next step, we combine again the lowest two more frequencies. So in this example, which is the next two lowest frequency here? Can you tell which two has the next lowest frequency?
20 and 23.
Yeah, 0.20 and 0.23. So we combine these two again.
0.43.
So in this case, it was ED and CED, right? We combine these together and we create one node. So, and like that, we keep on doing. Next two are A and B, right? This is 0.43. Next two lowest frequency are 0.32 and 0.25. So we combine A and B and we get 0.57.
Yeah.
Right. Now we stop. We stop when the tree is of length, when only two are there. When we find this structure, we stop. This is the stopping. So now here we have AB and CDE. So CDE is here
What is
and
our
AB.
what is your intention to do this?
Right, and I'll show that why we are doing this.
Okay.
Okay, so this is where we should stop it, like this. So this initially was this table we had, and we created this, right? So now we rebuild this tree again. Okay, now let me explain the theory part here. Okay. So from the this claim we had the leaves at the depth occur in pairs. So and they should be having the lowest frequency, right? The leaves at the depth are in pairs and should also have the lowest frequency. And then what we do is we pick so X and Y with the smallest frequency, and we combine, just like how we did in the example. We combined them and added their frequency, right? And updated the alphabet. Matlab, updated the total tree. We removed the individual nodes and we added the combined node. That is what this line is. We basically from the initial alphabet that we had, we subtract the individual nodes and we added the combined node. Basically doing this. This ED was the individual nodes.
Please again, set comprehension. What do you A such that X Y is minus A minus A minus.
Yeah, A minus XY. So A is the initial tree we had. This was if say this is A, and we were combining.
Okay, got it.
Yeah, so we are subtracting the individual nodes and we are adding the combined node to get this structure. Yeah, so that is that statement. After that, we keep on doing this recursively. Okay, so this part is the next. So after doing this, so So this structure is the base case. From here, now we build the tree. Like this, what we did is we combined the lowest frequency together, and we found out this final structure, right? So this has 0.57 and CDE has 0.43. From here, we rebuild the tree. So this is from here is what we are creating. So initial what this example I gave is we are trying to find this structure. This structure we are trying to find from this input. That is, this is the input we had. From this input, we are trying to create this tree, right? So I think this tree example is this is just for illustration I showed. What we have is A, B, C, D with the frequency. Using this, we are trying to build the tree, that binary tree with that leaf. So, by you combining, yeah,
This frequency will be given.
frequency is we can calculate the frequency, right? If we have this string, the string will be the input. This string will be the input. So
Okay. We will calculate the frequency from this string, and then we
yeah,
will make this table.
right. This table we can make. Once we have this table, we do these operations and we make this A, B, C, D with the frequency. Now with this, we will build the tree. So we have this structure here. Now what we'll do is we'll repeatedly split. So we first split the highest frequency. What AB is the highest frequency, we split it into, and then we split the other set. So we just keep on splitting it again. And finally, we'll get this tree.
This will be done for each string only, right? Particular string, no?
Yeah,
The
this
whole
will be
paragraph.
our
Only one string separated by a space, right? When a space is there, the second string will start. Is it so, no?
space. No. I didn't get that point.
A string. Suppose the
String in the
string we had. A string means this is a single string. Double A, double B, double C, A, E, D, right? Then
Yeah.
this option will be applicable for a particular string. Next string will come, then again it will be repeated. The same. Is it so, no?
No. So no, I think that is not what we. So we have this. This is the input, right? This is the input. We are
Yeah.
trying to encode this input. But in this way, for example, if we see this, there is 2A, it will be 1, 1, 1, 1.
Yeah.
B is 1, 1. Like this, we are trying to encode. But to encode, we need to find, right, what is this A representing? What is the encoded of A? What is the encoding of B? What is the encoding of C? This is what we are trying to find using this method.
Okay.
Using this Huffman's algorithm. So by finding this tree, we can, by repeatedly doing these set of operations, we'll get this tree. Once we have this tree, we can actually find out, right? Just like 0, 0 we did. Like that, using that, we can find this encoding.
Okay.
That is what this Huffman's algorithm is. So the next set are why this is a greedy, the proof of the greedy. The next set of slides, and this is the theory part. I think it will be better to watch the video. It is the proof of why it is this works, why this works.
Okay. In
So
the video,
let's direct. Yeah. So let's directly go to the coding, because the code is not given in the lecture.
Okay.
So this is what first we are given a set of input. So we first we first find the frequency, and then we combine the lower frequencies together, and then we get this structure, right? This one. From this we split and we build the tree. Once we have this tree, we can find the encoding by giving the left as 0, 1 or 1, 0, however you want, it doesn't matter. which any one rule you can use, using which you can get the encoding, the best optimal encoding. So this is the greedy way by which we use Huffman's algorithm to get the best possible encoding for any given set of inputs. So this is basically the logic of Huffman's encoding. Okay, I hope that is clear.
Yeah, clear. Please.
Okay, now let's move on to the first problem, PPA 1. Okay, so we have to write an Huffman, function Huffman S that accepts the string S. So S will be given, which will be of characters A, B, C, D, E, and F without any space. The function should generate the prefix code for each character based on its frequency in the string S and return a dictionary where the key of the dictionary represents the character and the corresponding value represents the Huffman code of that character. So we are given a class node also. We have to use this node as well. So the node has frequency, symbol is basically the alphabet, A, B, C, D, or whatever it is, and then a left and a right. We'll use this later on. So we have to select two smallest frequency nodes each time. If more than two nodes have the same smallest frequency, then select the node in the lexicographical order of their symbol. Assume that x and y are two smallest node, then if x dot frequency is less than 5 dot frequency, then x will always come on the left and y will always come on the right of the parent node. Okay. So, this will be the reverse of it. So here we had like this. So the lower frequency will come this side, is what they're saying.
Yeah.
If x dot frequency is equal to y dot frequency, then the symbol of node, which comes first in the alphabetical order, is what will become the left child, and others will become the right child of the parent node. If x is a left node and y is a right node, then the parent node will be identified by x dot symbol plus y dot symbol for further creation of the tree. Okay, so these are some rules we have. So this is the example. So in this example, A occurs 4 times, B2, C3, D7, and so on. And we have to generate this tree. So you can see that, so D is the smallest, right? D is the highest frequency. D occurs 7. So D and F. F is the next highest frequency. So this is the similarly how we represented before, right? So F and D are the leaf at the lowest level, followed by the others. A4, E, C, and
These are not on the lowest level, I think.
yeah.
D is at the lowest level of the boundary binary tree.
Not the lowest level. I mean the lowest height. So it is in the lower height, right? This is the lowest level. If you say this level is the
Third level. Second level.
Yeah. So this will be at a lower level in the sense before it, right? If you see the structure.
Yeah.
So these, since their frequency is more, we need lesser number of bits. So F can be represented using 0, 1. And D can be represented using 1, 0. Right? So the higher the frequency is, we represent them using lesser number of bits. So they will be on a
node values 24, 14, 7. This is the node values.
This is the combined frequency. So since here we have BC, this is the total summation of everything. Once we split BCF and DEA, BCF is B is 2, C is 3, 5 plus 5, 10, right? So this is the combined frequency of B, C, and F.
Yeah. At each level, it is equal to 24. Yeah.
Right. So as we split, we spread, yeah. So this is the rough structure. So we did not, so this is the output we have to give. So A is 1, 1, 1. A is represented by 1, 1, 1, right? B is represented 0, 0, 0. B here, 0, 0, 0. So this is the output we have to give. The number of bits, the encoding what we are using to represent each alphabet should be our output.
This 1 and 0, how this 1 and 0 came? Based on the frequency.
Yeah, based on the how we in that lecture slides we formulated, right? We first combined and then we expanded the tree.
Okay.
At the end, we
This is a
find
standard structure. Left will be 0, right will be 1.
right. That will be given, right? In this, there are certain set of rules, so we have to follow that rule. If it is given the other way around, you can use that also.
Okay.
Right. So this is the class node is given, and we have the Huffman function. Okay. So we have the this Huffman function we have to write.
This is initialization part, na? Non-left frequency.
Yeah, this is given to us, right? We cannot we have to use it. So in the question it was given.
Yeah, I want
So
to
we have
understand that.
This is just a class. Frequency is the frequency we have to calculate, and for every node, so this is the node, right? So for example, for this node, the frequency is 2, the symbol is B. Similarly, for this node, the frequency is 24. The symbol is B, C, F, D, E, A.
Yeah.
Then the left and right, we give the left and right. So left is BCF, the right is DEA. So once we use this, so this node class we have to use to find to create this binary tree.
In the code, we are assigning none for both, na? For frequency also, for symbol also.
Yeah.
Initially,
That. Yeah.
Initially, it is none, na? Frequency and symbol, both is none initially.
So we are given this S, right? The string we are given, from that symbol is basically the alphabet, right? The alphabets B, C, or the B, C.
Go to the first line of the code. Given. Yeah. Initialization part.
Oh, initially you are saying, okay, when we create a node, yeah, it will be initially. We'll give.
Initializing, frequency is none and symbol is also none.
Right. So I'll show you how we have to first initialize the node, and then we have to connect them using the left and right. Okay, so let's start solving it. So maybe then it will be more clear.
Yeah.
So this is the function we have. So we have to give a dictionary, right? Output should be a dictionary with the symbol and the encoding. So let's initialize let's call it a Huff code dictionary. This will be our output. Yeah.
Output.
Okay. Right. So S is our given input. S is a string, right? Let's just print and see what S is. Let's try to print it. So this is S. S is a string. These are S. So let's convert S into a list. This is just, I'm just converting S into a list. Okay, so it will just spread out everything. And then we'll take the unique characters from S, making it a set. So I'll just print this and show you what I've done here. I'll also print char. If you see, what I've just done is I've just first the character is just the input, whatever I'm getting, I'm just spreading it into a list of each, just a list spread, and then the unique part is we are just setting like we are removing the duplicates. This is just removing all the duplicates. I hope that is clear.
No, so once again, sir, I connection was please.
Okay.
My code is
So we are given a string, right? Yes, we are given a string. First,
yeah.
I'm just making that string string into a list. That is, if you see here, the
separated
list.
separated by comma.
Yeah, right. So I hope it is visible. This one.
Yeah, very visible, sir, visible.
Right. So that was character, and then the unique character is just the set of all the unique letters in it.
Yeah.
F, B, C, D. Yeah, that is all what it is. Okay. So now what I'll do is we have to find the frequency, right? Let's call it frequency list.
This could be done by the set function, no? Set char will give remove the duplicate. Is it so?
Right. Set will always only have unique
Okay.
characters. Now we'll find the frequency. So for C character in this unique.
Yeah, unique char.
In the frequency list, we'll append. We'll make a tuple. First one will be I'll tell you what this is. See, so this will be a tuple. The first part of the tuple will be the count of that character, and the second part will be the character itself. I'll just print it and show it. Make it more clear. If you print it. Yeah, so E happens 3 times. So the count of E, count of B, D is 7 times, and F 5. So that is what it is. Frequency followed by the character. In a tuple, a list, it will be a list in which the tuples 0th value is the frequency, the first value is the character. That is what a frequency list is. And now what we'll do is we'll iterate through this frequency list. Okay, so we'll also need a nodes list. I'll tell you why we are using this. First, we'll create a new node. This node will be item 0, 1. So what this is, we are creating a node with frequency and the symbol. So if you see the class node, we have to give input as frequency and we are giving a symbol. Left and right, initially it will be none. So if we are not giving any input also, it will take it as none. So this is, we are creating a new node with the frequency and symbol as input. So item 0, as we saw in the frequency list, is the frequency. Item 1 is the character, whatever the symbol character is. So we are creating a new node. I hope this is clear.
It was initialized. Initially, it was left or right. This left right was initially none. Okay, now we are filling this in the frequency list, right? Every node, every
No,
new
no.
node.
No, new node is just basically we are initializing a new node, one node. We are creating a new node
Yeah.
with the item 0 will be the frequency item. For item in frequency list is basically the frequency list we created. We are iterating through the frequency list. This is the frequency list which has
This node
tuples.
is an object. This node is an object of the class node, no? This node.
Right, right. Yeah. So we are
Right.
giving
Yeah.
the
Yeah. Item
yeah,
0 and item 1 is left and right. Left and right. Correct.
no, item 0 and item 1 are frequency and symbol.
Yeah. Frequency. Char dot count C. It will be synonymous with that, right? And C will be that.
Item 0 is the frequency, item 1 is the symbol. Left and right, we are not giving any input because initially there is no left and right. So what we are doing this is we are creating these set of nodes, the bottom nodes. So these doesn't have any left or right. They only have their frequency and the symbol. So these are what we are creating, the bottom nodes. Here. Okay, so after this, what we'll do is we'll append this into this nodes list. The nodes list we have created, we'll append to that as a tuple. That is item, comma, new node. So this new node we have created, will this nodes list, we'll input it in here. Let me just show you what it looks like.
So how many elements an item in will have? An item will have two elements, count and the character itself. Is it so?
Right, right. This item will have count and zeroth will be the count, 1 will be the character.
And new node will have again two elements.
The new node is a node we have created with the input frequency and symbol. That character count is the frequency, symbol is the character. There is no left and right initially. So let's just see what it looks like.
Yeah.
Yeah, so this, so don't focus on these, just focus on this. So this is what it is. So 7, D is the item. That is the
frequency in the track list.
Frequency and the character, followed by the object, that is the node. So this is how it shows. This is actually the node. Followed by the next frequency and the symbol, followed by the node. So that is what this has.
What is the node exactly coming? What is the node coming?
Yeah, so
value of the node.
Yeah, this is just showing the memory location of it. So it just shows.
Yeah.
So we don't need to know what here. No, we only need it for the code. We don't need to print that, right? So this is just for illustration I showed. We'll not be printing the node. We'll only use the node to.
If you want to print, then what will be printed as a new node?
We'll have to write. we'll have to write a new function, right? Inside the class.
Can't we print here? Print frequency, comma,
Yeah,
symbol.
we can actually do that if you want. Nodes. So for that we have to iterate. So we can print like this. New node dot frequency. You are saying, right?
Yeah. Yeah.
Like that you can print. You put it in a print statement.
Yeah. Comma.
Yeah.
New node dot symbol.
Right. So we can actually.
It will print, na?
It will.
Let us see. Okay. Just to know okay, how it is working. Okay.
Sure.
Okay. Got it.
The frequency and the symbol.
Mhm.
Okay. So after this, so we have. Okay, I'll remove this also. Don't do that. Now, so we have created the node list, right? With the initial set of values, the bottommost nodes. So now let's just iterate. Now I'll create a while loop. So this while loop. So I'll show you why I'll tell. So when the length of this node list is greater than 1, so I'll this while condition I'll explain later on. Okay, first let me fill in the inside part. So first what we'll do is we'll sort the nodes list. So this was the nodes list in which I think so the nodes list was not sorted according to the frequency, right? This nodes dot sort will sort it according to the frequency, because frequency was the first this, right? If we just print dot sort.
Yeah.
I think there is a network problem. Can you hear me?
Yeah. We can hear you. Portal problem is there. Network, internet is good. Portal problem.
Okay. Let me just refresh. Okay.
While loop is running.
Oh. Oh, right. Oh, correct. Okay. So okay. The nodes dot sort is not, it doesn't give any output, right? So we have to first sort it and then print it. That is why the none type object was given. So if you do like this, then we'll see the sorted nodes, because this doesn't give any output. So now you can see, right, the lowest frequency will come before. 2B is coming first, then C is 3. So it is sorting by the frequency. And also the alphabet. If the frequency is same, then it will go to the next tuples, next. It sorts by if C after CE comes, right? So this will give us sorted nodes list. Okay. So after sorting, what we'll do is we'll create the left and right. So left is nodes. 1. Okay. So nodes of 0 of 1. Do you know what that is? So this is the nodes we had. Nodes of 0 is a tuple, right? So this is the tuple, nodes of 0. And then the 1 is the symbol, right? The character. Is this understood?
Yes.
Oh, no, I think I made a small mistake here. So nodes of 0 is the first node, right? First node, the node with the lowest frequency, and the 1, the nodes of zeros of 1 is the first nodes, this node, the object node object is what we are accessing. The right is the second lowest. So 0 is so since we have sorted it, so the 0 is the first set of node. The 1, so this is basically what we are extracting is the nodes list is actually carrying node of 0 is a tuple followed by the object of the class node, right? Which has the lowest frequency. And node of 1 is the second lowest frequency. And we are and the 1 will give the node object which we have created, which is there in that nodes list. Okay, now I'll tell you why we are doing this. Now we'll create a new node again. This time we'll create the node with the frequency L dot frequency this plus R dot frequency comma L dot symbol plus R dot symbol L comma R. So this, what we are doing is we are combining the lowest frequency nodes, and we are making a combined node by combining both left and right. That is the two lowest frequency nodes we are combining together and creating a new node. This is what we are doing here.
No, I did not get it. Last line 29.
So here initially we had these, right, and their frequencies. So we had sorted it according to their frequency.
Yeah.
Now what we are doing is we are combining so this was the so we are taking this object. So L is equal to nodes of 0, 1. Nodes of 0 will be the first
element in that.
Yeah, in that nodes list, right? First element is basically one tuple, which is the frequency and the symbol, followed by the object of the node class.
Yeah.
So we have this L is what? So node of 0, 1. So 0 is the tuple, 1 is the object of that node, right? So we are initializing L to that node. Basically, the node with the lowest frequency. And R is the node with the second lowest frequency. Right, so we had to combine, right? Initially, we had this list. We had created all the nodes. Here, we have to combine the node with the lowest frequency and the second lowest frequency. This combination is what we are doing. So we are creating a new node with the combination of the lowest and the second lowest frequency. So like in this example, we are combining the lowest and the second lowest frequency together and creating a new node with the combined the combination frequency. We are adding both frequency together. That is what the frequency we are summing up together. We are concatenating the symbols also together. L dot symbol plus R dot symbol basically combines both the symbols together. And then L and R we are giving the left and right. So this time we are giving when we are creating the new node, we are giving the left and the right also as the L and R. That is what we are doing here. I hope this is clear.
Yes.
Now from that initial nodes, we remove the 0 and the second. So this will just remove that two L and R we just used, right? The lowest frequency and the second lowest frequency nodes which we just used to create the new node. We'll remove them from the nodes list. And now what we'll do is we'll append
2 times pop to remove 2 elements from one node.
We have used the lowest and the second lowest frequency, right? Frequency nodes. So we are removing both of them. Just two, because the nodes list was sorted. It had the lowest and the second lowest frequency in the 0th and first position, right? So we are first, yeah. So now what we'll do is we'll in the nodes list was in the form of a tuple, right? So in that tuple, first we'll frequency was the first one. So frequency plus R dot frequency. Now we need the symbol L dot symbol plus R dot symbol. And now we need the. So this is the nodes list, the nodes list we had, right? After combining them, we are adding it to the list. So the list was in the form of a tuple followed every element in that nodes list was in the form of a tuple followed by the node object of the class node, right? So after combining the two lowest frequency nodes together, we are creating that combined node we are adding it to the nodes list. I hope this is clear. If I just print it, then maybe it will be easy. Print. Or just I'll print the nodes list. So let's just see. Okay, I've made some.
Am I audible?
Yeah. You're audible. You can hear me, right?
Okay.
Right. So here you can see, right? We have kept on adding, combining them and adding to the nodes list and the object node we have created. That's what we are doing. We are appending it to the nodes list. I hope this is clear. Is there any confusion here? So by doing this while loop, we have done this part of the code. That is the combining everything together till we only have 2. So this exit condition, length of node is greater than 1. So this is the exit condition when we find this.
Which one we find? Greater than 1.
Yeah.
Right. And when we will get this greater than 1? Last one. When
Uh,
the
uh,
last
right. So you,
base of the tree will be achieved, right?
yeah, the base condition, the base final condition we had, right? This condition.
Right.
So we have done this part. Now we have to expand it to make it the tree, right? So now is the part which, so this while loop, after this, we have to expand it again. So basically we have to find the Huffman code for each character. So let me show you how to do this. So we'll take for each character in the unique list. What is the unique character list? We iterate through all the characters in the unique character list. Uh, so now, okay, let me just write this part of the code and then I'll explain it. We'll do this first and then say the code is an empty list, empty string. Um, okay, I just explained this part of the code after I write it. So I'll just write the. Okay. So this part of the code is trying to figure out the encoding of each character. So I'll show you what it is doing. So let me just check, show you this. Okay, so uh, okay, right. So this new node, that is the last. So we are using this new node. That is this new node that we have created at the end of the while loop. So at the end of the while loop, this new node will have the entire string, right? B, C, F, D, E, A. It has combined everything together and it has this full node with the frequency 24 at the end of the above while loop, at the end of this loop. So that is what the new node will have. So we first initialize this temp to that new node. And we are so what we are doing here is so while this so character unique character has all the unique characters in it, like all the, so we have already created the unique character, we have seen it, it has all the unique, so we are iterating to every character, every unique character of the list, and then so so this temp will so we are trying to unravel, right? Once we have this we are trying to split it and make it into uh, this structure, the leaves of the tree. So how we do that is so as long as this is the exit condition, so we uh, so the left of the temp initially will be this BCF, right? The BCDE is left will be BCF and the right will be DEA. So if we are going to the left side, then we have to give it 0. The encoding is 0. If we are going to the right, the encoding is 1. So whenever we go to the left, every time we go to the left, we add in the encoding, we add 0. And we the temp, which was initially the full set of node, the we reduce it to the left node. That is, the left node is BCF. So the BCFDE is left was BCF, right? That is how we have initialized the node class. It has left and right. So after adding this 0, we change the temp to temp dot left, and then we keep on doing it till the character is not found. The character is like, that is the only character remaining. So basically what we are trying to do is we are trying to build we are trying to find this encoding. So if it is going to the left side, we add a 0. If it is going to the right side, we add a 1. Again, if it is and then if for example, if we are trying to find the encoding for B, so we start from here. When it goes to left, uh, we, uh, we add a 0, then we check here, and then it again goes to left. We add a 0 again, and it again goes to left, and we add one more 0. So by this, we find the encoding of B is 0, 0, 0. If it was C, we first go left, left, and right, and we append. So this is what this while loop is doing. So for every character, it is checking whether it is equal to the symbol or not. I mean, it is not. So, so if it is on the left side, so temp dot symbol will hold the symbol, right? If that character is, if we are finding the encoding of C, we first check whether C is there on the left or on the right of the initial node. If it is on the left, we go to the left, and then we again check if it is on the left or not. If it is on the left, we go here, and then we find the right. So that is what this while loop is doing. So it is unraveling the initial what we have initial nodes we have created. We are just unraveling it and giving this encoding. Basically, if it is on the left side, we are adding 0. If it is on the right side, we are adding 1. Like that, we calculate the Huffman code of each character. Uh, is this clear, or is there any doubt on this? Let's just see what the output is. Oh, I did something else. Okay, this is working. So, like, is there any doubt on the final part of this code? I can explain it again, I think. Or did you understand? Like, did you get this part? What we are doing here? I cannot hear. Okay. So is this understood? What we have just seen in the slides, we have just done it through code. So the initial part of the code, we are using the given node structure. So to first we initialize all the leaf, like all the like unique characters, right? We give it a node, we don't give them left or right. And then we keep on combining the lowest, but first we sort the nodes that will give us the lowest frequency uh, nodes first, right? So we take the lowest and the second lowest node, and then we create a new node by combining their frequency and their symbol and giving the left and right. So the left will be the lowest node, and the right will be the second lowest node. Like that, we create this chain. So this the from line 25 to 32 is just this part. We have this initial unique list and the frequency we use convert it into that class object of the class node, and we create this after and then we combine this as well. It is not just this, we do one more step, that is a b c d e c d e, we combine that also, and we add their frequency as well. There is one more step in this code, and we create this final bcfdea. But every node, right, every node, these nodes has the left and right information as well. So once we have this, what we do is we take every character from the unique list. That is, we take every character from the unique list and we check whether that character is on the left part of the node or on the right part of the node. If it is on the left part of the node, like left part of on this node, then we add a 0. So if we are trying to find f, so if it is first, it is on the left part, then on the right part. So first we add a 0, then we add a 1. So we get this encoding as 0, 1. Similarly, if we are trying to find E, so E is on the right part, right? So it is on the right part here. Here also it is on the right part. Here it is on the left part. So we get this encoding 1, 1, 0. Because that is what we initially created using the first part of it. So we are just backtracking this time, adding the code to it. So if the character is not in the temp symbol, we exit the while. I mean, if yeah. So this is the basic how we do the Huffman codings. This is the Huffman. This is generally the Huffman codings algorithm. You can call it using this node structure that is given to us. Okay, so I think we have covered taken a lot of time for this. So maybe we'll just quickly go through the next PPA. So second PPA is on minimizing lateness. I'll very quickly explain what the logic is. I'll not go very deep into it, and then we'll try to code it. Let me just. Yeah. So minimizing lateness is basically, just take this example. I hope this is visible to everyone, right? Okay. So minimizing lateness, for example, if IITM has a 3D printer and a number of users need to use this printer, like certain number of users need to use this printer, and there is a deadline for, so for example, if one user takes time ti to print something from this 3D printer, but that user also has a deadline di. Within this deadline, he has to complete the printing, that task which he has. So we have to find the like minimize the maximum lateness. So for example, there are certain set of users. So each user takes Ti time, but also has a deadline Ti. So like that, there are many users. So we have to find a greedy strategy by which we minimize the lateness, the maximum lateness possible. We minimize that. So that is the minimizing lateness part of like why we are doing it. So there are a few couple of strategies given. The strategy one. The first strategy is we schedule the request based on the length, the time required to. For example, if there are two users who want to use, we schedule them. Whoever like starts before, like whoever has uh, so if T1 has 1 and T2 has 10, we schedule the request based on the order of length of time. So how much time they are going to use. If so, whoever has the greatest more time, we schedule them based on that. That is the first strategy. But this strategy does not work. Okay. So the reason so is if, for example, T1 starts at 1 and has a deadline of 100, but T2 starts at 10. I mean, the time of T1 is 1 and the deadline of 1 is 100. The time of 2 is 10 and the deadline of 2 is also 10. In this case, if we allot based on the time, if we allot T1 first and then we allot T2, so there will be a lateness of 1, right? In this case. Are you following what I'm saying? Uh, okay. Right. So this strategy does not work because of this. We can find this counter example that if someone has a lower time but a higher deadline, but if we schedule them based on their order of length, then this strategy does not work. Similarly, if we give the priority based on the slack time, that is deadline minus t time they take. If we use this also, it does not work. We can see counter example to it also. I think this part is much explained in the lecture. It is very easy. You can easily grasp this. So the strategy that works is for minimum lateness problem. The strategy that works is you have to schedule them based on their increasing order of deadlines. So whichever job finishes early, you give that printer to them first. Then the job that finishes next, you give it to them, and so on. This way, there will not be any idle time between any jobs, and so this you can prove that this is the correct greedy strategy of on this particular situation. That is minimizing lateness problems. You schedule them based on their increasing order of deadline. So this is how we do it. So the next part of these slides are just to prove of how it works. That is just the rest part of the slides. It is also explained in the in the video as well. So you just have to understand that the strategy, the greedy strategy that we use in this case is we schedule requests in increasing order of their deadline. So this is what we do for minimizing lateness problem. All the minimizing lateness problem, we schedule the request based on their increasing order of deadline. So just remember this, and let's quickly do this PPA. So the PPA is a manufacturing plant has n independent working lines. Each job requires different amount of time to be completed and due time. Optimize the scheduling of the job for every line so that every job will be completed within due time or minimum lateness possible. So we have to write a function, minimum lateness, which has n and jobs. Okay, so n is the working lines, and jobs are all the jobs. We'll see that input later. So this is the function we have to write. It will return the sequence of job IDs to be scheduled in a list of list. So the jobs is a tuple which has job ID, time required, and the due time. That is the deadline. The job ID are the unique number of assigned job. Time required is the relevant time required to complete the job, and due time is the absolute time before which the job should have completed respectively. So there is this job ID is given from 0 to m-1 for m jobs. So this is how we calculate the lateness. So lateness of I is if the delivery time, so if the time is greater than the deadline, that means we have some lateness, right? So we just subtract them to get the lateness. Otherwise, it is 0. So for each test cases, there will be an upper bound of lateness. Okay, so there will be an upper bound of lateness as well. This will not be given as input. They are only given n jobs. Okay, so the input we have is n. Okay, this is not the input. So we have to write a function, minimize lateness with n and jobs. So n is basically the independent working lines. So many working lines are there, and we have a certain set of jobs, right? 0, 1, 2, 3, 4, how much ever it is. So that is for this tuple, the first 0th element of the tuple is the serial number. Second, first element is the time it requires to run this job. Job 0 takes 10 time, and its deadline is at 15, time 15. Similarly, for the other set of jobs. So the job 1 takes 9 duration. The deadline is at 15. You have to finish it before 15. Otherwise, if we exceed, then there will be lateness. So in this case, we are given 2 lines. 2 independent working lines are there. And we have to arrange these jobs in both the lines such that the upper bound of lateness, the 36, the lateness should not be greater than 36. Upper bound. So this will be the output. So if we see from here, we use the greedy strategy. In the greedy strategy, we read the line, right? So we scheduled requests in the increasing order of deadlines. This was the approach we used for minimizing lateness. So if we see, first we see the deadline. The minimum deadline is for 5. Is for the serial number 8. 8th job has a deadline of 5. So if we add that first to this list, then we see the next lowest line, lowest deadline. That is the 4 and 6. So you can add them anywhere. You can add them in the, either 4 or 6. You can add here. So now one has 8, one has 6 in it. Now we check the time for the job. 8 takes 3 duration, right? And the job 6 takes 2 duration. So this line will finish faster. So now we'll add the next job to this line. That is job 4 is the next lowest deadline. So now we add it to this second line. So now this line has 6 and 4. This line only has 8. So now we see the time for both. So time for this is 3. It will finish at 3. This will finish both 6 and 4 we have to add. 6 is 2, 4 is 5. That is 7. So this line will finish faster. So now we add the next lowest to this line, and then we check the time and we keep on doing it. This is the crux of this problem. I hope that is clear. If there are any doubts,
Yes.
please. Yeah. Okay, so that is how we have to separate. So minimum lateness. This is the crux of it. So this is the input we are given. So now let's just write the code for this. Okay, so this is not that difficult. I'll just explain what we are doing. I'll sort the jobs by the due time. Let me increase the size. So jobs is our input. So jobs was, if you remember, jobs was a tuple which had first job ID, then the time required, then the due time. You have to sort this job by the due time, by this due time, by this. So how to do that? So there is this a way to do this. Let's call it sorted jobs. We'll use the sorted function. This function, we can give it like this. Use the key. Right, 0, 1, 2, yeah. So this is basically what it is doing is it is sorting by third value of the tuple in jobs list. So if we just print this. Yeah, so 5 was the lowest job, 6, 6, 7. So this is how it is sorting it. Right, it is sorting based on the third, the second 0, 1 to third value of this tuple. It is sorting the jobs list, and we are putting it in the sorted jobs list. Okay. So after sorting, we need to find the list of lists, right? So let's keep we'll call it optimum list, or we'll just call it optimum jobs. This is just the list of list. We'll just initialize it because so that this is basically the lines, right? So whatever the n that, so these many lines we have, whatever the n we are given, that many lines we'll have. So that many list of list we'll have. So we'll initialize this optimum jobs based on the range of n, whatever the n is given. So in the first example, there were two conveyor lines, two lines, right? Whatever they were. Manufacturing plan has n independent working lines. We are just initializing these working lines as a list of empty list. Two, so based on the n, we'll initialize this. Now we'll keep track of the total time. That is, we'll keep it as a dictionary. So I range. This is just a dictionary to track time of each job line. So in the initial example, we had two job lines. So initially we'll give it 0, and we'll so this is basically is to be. If there are any doubts, right, please let me know. Okay. So if we just print this. Yeah, so in the first example, there were two lines, right? So we just create 0 and 1 and initialize it to 0. A dictionary with 0 and 1 and initialize it to 0. That is all what we are doing here. Okay. So this will just keep track of the total time. So I'll just so we'll be using a while loop. I'll just so I'll tell you why I'm using this I. So while I is less than uh, so I is initially 0. We'll keep on incrementing I. As and when we add a job to the lines, right? So we'll keep on adding a job to these lines. So every time we add, we'll increment the I. So when I reaches the length of jobs, we'll exit. So when I reaches the length of the job, we'll exit this while loop. That is basically we have added all the jobs. So that is what this I is representing. So let's find the next line where we have to add. So this will be total time, minimum of total time, but okay. So what we are doing here is we are finding next line in which we have to add with the minimum total time. The total time we have calculated, whichever has the minimum total time, we are adding. We will add to that next. So we saw in this example as well, right? Whichever had the minimum total. So initially it was 8 and 6, but then we checked the total time. So six. So this conveyor was this line was smaller. So we added next smallest 4 here. So we are keeping track of that total time. So the total time is basically a dictionary, right? So we check the value of the dictionary. Whichever has the lowest value, we find that line will be the next line. So this line is basically finding that next line by checking the minimum of values of the total time dictionary. So once we find the next line, what we'll do is we'll add to the optimum jobs, right? Optimum jobs. In the optimum jobs, next line, what append, sorted jobs, right? Sorted jobs. Okay, so what we are doing here is we are adding next job to the line with minimum total time. So in the optimum jobs, we had we had like based on the number of lines we have initialized the optimum jobs based on it. So so we find the next line, which line we have to add. In that line, we append the sorted jobs I comma 0. The sorted jobs was basically uh, uh, jobs was basically at this tuple, right, of job ID, time required, due time. We add this job ID. This is the zeroth element, the zeroth element of the tuple, right? So that we add it. So sorted job I of 0. That is basically so that is the in the sorted job list that this is the next the index this job ID of the so this is the job ID. So we add that ID which has minimum total time. I hope this is clear. What we are doing here is, in that, once we find the next line, we find this, the I will be, sorted jobs will be in the sorted order, right? So I will be, so first we find, so I will be at that so this will be sorted order. So I will be the next smallest job with the next minimum lateness. So we add. So basically, that is what we are doing. We are adding the next job to the line. So from the sorted jobs, we are finding that next job. Sorted job I comma 0 will give the ID of that next job. I hope this is clear. I think this is correct, but it is not entirely represented. After this, we'll increment the total time as the sorted by 1. So the 1 is the time, right? So the jobs of 1. So this was the time. So this we increment. So whichever job we have added, so whichever the minimum the jobs with the minimum deadline, the next set of jobs with the minimum deadline we have appended to the optimum jobs list. After that, we increment its total time as well, so that in the next iteration we can again compare, right? We find the minimum. Now we just increment the I and we return. Yeah. I hope this code is clear. Is there any doubt? This is just a straightaway code of what we are doing. We are just finding the minimum. We are first sorting everything by the minimum deadline, and then we add it to the first list, and then we check the total time of that list, and then if whichever has the lowest total time, we add to that list. So we just keep on doing this till all the jobs are we have seen all the jobs. So since sorted jobs, the sorted jobs is the sorted job, so I of this sorted job will be the next job that we have to add. Next minimum deadline job. The job which has the next minimum deadline will be in the ith position, because we are incrementing, and it is in the sorted order. Okay, I hope. Is there any doubt on this topic?
No, sir.
Okay. Then, if there is any more doubts, you can please ask. Otherwise, we can end the session.
No, sir. Thank you, sir.
Thank you. Thank you for joining, and have a good evening.
Good evening to you.
Good to have. Thank you.